Here is part B. Our parametric equations are x equals 4 plus 2 cosine theta and y equals sine theta. And you notice we are using theta here as our parameter, which is very common when you work with sine and cosine or trig functions. You could use t, of course, but it's not uncommon to see theta. All right, x equals 4 plus 2 cos theta, y equals sine theta. The directions were to sketch the curve, then indicate the orientation with arrows, and finally write the Cartesian equation. So we'll begin, of course, with the curve. What are we going to do? Same approach as the last problem. We're going to get this table. I'm going to try and not show you the graph itself. So I'm going to have theta, x, and y. Again, I chose 5 values of theta, and what's really great about sine and cosine, let's just go through a single period. So let's start at 0, pi over 2, pi, 3 pi over 2, and 2 pi. If you wanted, once you pass 2 pi, there's no reason at all to keep going because you'll have gone through the cycle. If you wanted to fill in more details, in between pi over 4, pi over 3, and kind of fill in more points, you could certainly do that. But generally I find 5 points is plenty enough to see the curve once you have those ordered pairs plotted. But sometimes you plot those and you're like, that's not good enough, and you go back and you get more, right? Okay, so for 0, pi over 2, pi, 3 pi over 2, and 2 pi, we're going to plug those in, get the x and y values for each one, and I'm just going to show you all this right here. And we can talk through some of them, right? So theta equals 0. Well, cosine equals 1. So we get 4 plus 2. The x value is 6. At theta equals 0, well, sine of 0 is 0. So there you go. And our first ordered pair will be 6, 0 on our graph. Then pi over 2, well, cosine is 0, so we get 4. Sine is 1. And okay, I'll let you think through the rest of them. When we get to 2 pi, we come full circle and we're back to the same point that we started at. All right. So, all right, I'm going to show you the graph now with the arrows, but we'll talk through it. Turns out it's an ellipse. But let's see it all in detail. Okay, so there's the point 6, 0. My x-axis, right? My y-axis. 6, 0. And then 4, 1. And then 2, 0. Then we start to come back the other way, 4, negative 1. And finally, back to 6, 0. And so we can see those. Well, the 5th point ended up being the same as the first point, so there you are. And we can tell how we moved, right? Once we draw that curve, then we're going in that counterclockwise direction, right? So you got my arrows there as well. And then you take a step back, like, oh, that's an ellipse. Oh my goodness, like these parametric equations with sine and cosine produced an ellipse. That is pretty cool. Now here's one big takeaway as well that you might not have noticed yet. That's not a function if you just think of it in terms of x and y, right? Doesn't pass the vertical line test. But if you think of it parametrically with this third variable theta, we can think of it as a pair of functions. And so the rules for derivatives and that sort of thing, we don't have to rely on implicit differentiation. That really, really is a sweet breakthrough to think of non-functions. Not only do we get more information, right, like where is a particle or a projectile or who knows what might be going around in circles, a planet, I don't know, any kind of satellite, where is it at any given period of time or angle? But then also we're treating it like two functions, and when they come together, they make something that originally would not have been. Okay, so you're blown away by this. What's next? We got the curve, the orientation. We need to write the Cartesian equation. Okay. Well, there's kind of two ways to write the Cartesian equation. One, you might be able to get the Cartesian equation just by looking at the graph. Maybe you remember the basic form for the equation of an ellipse, and you could get that equation of that ellipse in terms of x and y just by looking at the graph. But maybe not. So I want to show you a pretty cool method here. And even if you could get the equation from that graph, even so, this is pretty sweet. So the Cartesian equation, we're going to use that identity, cosine squared theta plus sine squared theta equals 1. Very different approach than the way we did part A, all right, where we had the polynomials. Sine and cosine, take advantage of this. So we had x equals 4 plus 2 cos theta. We had y equals sine theta. Turns out we don't have to do anything with y equals sine theta, but over here, let's isolate cosine theta. Okay, so subtract the 4, divide by 2. I know what sine theta equals. I know what cos theta equals. And then I'm going to do a substitution. I'm going to put x minus 4 over 2 in for cosine. I'm going to put just y in for sine. And there, I've got it. The Cartesian equation. Now, usually the ellipse, we write it a little bit differently. We go ahead and square that denominator. So there it is, x minus 4 squared over 4 plus y squared equals 1. That is the equation of the ellipse we saw a moment ago. It uses that identity. Isn't that crazy? Okay. Pretty sweet. All right, we're going to now see another style of example. Now this one involves another conic section, this time the hyperbola, but definitely more challenging. So it says find the parametric equations for the hyperbola with vertices 0, plus and minus 1, and foci 0, plus and minus 2. This is like the opposite problem. We're given some information about the hyperbola, enough information so that we could get the Cartesian equation, and then we're going to work backwards and find the parametric equations. All right, hold on. How are we even going to start this? All right, well, we're going to find the Cartesian equation for that hyperbola. So you might have been a little while since you've thought about equations of hyperbolas. We really don't do that in Calc 1. It's been at least since pre-calc, however long ago that was for you. So I don't want to reveal everything. I just want to start by, let's just graph, what we know from what they tell us. That's going to be really helpful. Just a sketch. So it's a hyperbola. Okay, they tell us the vertices are at 0, plus and minus 1. So 0, 1, 0, negative 1. So we know as soon as we know these are the vertices that the hyperbola is going to open upwards and downwards, right? Because they go opposite of, their relationship to the other vertex. Also, this, you don't really graph so much this, but the foci are at 0, 2 and 0, negative 2. So the foci, the idea is that point is dictating just how sharp or how narrow or wide, these two arms of the hyperbola are. So if it's further away, then this thing gets wider. If it's closer, then it gets more narrow. Now that really doesn't come into my sketch, but I'm just going to note 0, 2, 0, negative 2. Okay. So now how do I get the Cartesian equation for such a hyperbola? Let's start with just the general hyperbola in this form. Again, maybe it's been a few years. You might not remember this. It'd probably be easier if we were all in class together. And I could say, anybody remember? And maybe one person would, right? Okay, so here it is. In this form, because it opens upwards and downwards, the y comes first. So we have y minus k squared over b squared minus x minus h squared over a squared. Very similar to the ellipse. Big difference is you subtract. But as soon as you subtract, now the order matters. Is the x coming first or is the y coming first? Well, if it's opening vertically, the y comes first. Okay. Also, the other aspects, the hk, that's the center of your hyperbola, the point right at the middle, in between the two arms. And then the a squared and the b squared relate to the distances from the center. So we're going to see that here in a moment, how this plays out. Okay, but that's the general form. Do we know any of these values, right? We need to know h, we need to know k, a, and b. If we know those four numbers, then we got the Cartesian equation and we can move on from there. In this case, yeah, this sketch is really helpful because we do know where this hyperbola is centered. It's centered right at the origin. It's all symmetric about the origin. So we know hk immediately. hk equals 0, 0. So that really makes our work a lot simpler. 0, 0 for hk. Turns out we know b as well. b is the distance from the center, the vertical distance, to your vertex. Well, how far is it from the center to each vertex? We think of it as a positive distance, right? We know b equals 1. Oh, this is great. The only unknown is going to be a, and that's where the foci are going to come in. Okay. But this much we can tell already. All right, so we got this question, like, what is a? Now again, this goes back to solving for a. There's a particular relationship you have to remember. So a is going to be a horizontal distance because it's connected with x. It's a horizontal distance that you would walk out. And maybe you remember, like, you would draw like a little box is the way most people teach it. So you would move up the 1, and then a, you would move out, and then you would draw the asymptotes connecting the corners of the box. Most people learn it that way. We still teach it that way. Okay. So a is that distance from the center out here, that where you would draw that box, and then these like tend toward those diagonal lines. So as soon as you draw that box, you realize, oh, that creates like a little right triangle, right? Okay, so Pythagorean Theorem comes into this. Here it is, c squared equals a squared plus b squared. All right, so, okay, all right, what's that all about? Well, we know what b equals. It was 1. Turns out c is the distance to that foci. So that distance right there, and my box is not perfect, but if you swung it up, it would actually be the same as the distance to your foci. Okay. Interesting. I think I should make mine a little bit wider. So we know c is 2, b is 1. We can easily solve for a. It's the square root of 3. And now we can plug all this in, and we have the Cartesian equation. 0, 0 for hk, b is 1, a is cube root of 3, but we're going to square it, so we get y squared minus x squared over 3 equals 1. Again, the Cartesian equation. Now, we're going to somehow figure out parametric equations for this Cartesian equation. Now I need to go to the next page. How are we going to do that? Check it out. We're going to use a different trig identity. This time we want the tangent secant one. 1 plus tangent squared theta equals secant squared theta. Why do we want that? Because we can get it to match the pieces of that Cartesian equation. Okay, how so? Because we're going to write it this way. Subtract the tangent, and then, I reverse the order. So secant squared theta minus tangent squared theta equals 1. That's what we saw a moment ago, right? Y squared minus x squared over 3 equals 1. This trig identity is connected to hyperbolas. Isn't that crazy? All right. If we match, hey, what does y equal? Secant theta. How about, oh, well, this one we got to be careful with. We should think of it as x over root 3 quantity squared. Okay, so there we go. I wrote it there. So I've got immediately y equals secant theta. X over root 3 equals tangent, because we'd go back and square. And so we need to solve that for x. X equals cube root of 3 tangent theta. There are our parametric equations. You could check that in Desmos if you wanted to. Of course, this is your x, so put that into your x coordinate. That's your y. Put that into your y coordinate. You'll have to adjust. Let me pull this up a little more so it's a bit more clear. It's a little fuzzy. You'll have to adjust the values of t. If you make it t go from 0 to 2 pi, you'll get the full cycle. You'll see the full graph. And you notice Desmos is not going to know what you're doing if you put theta in there. So you need to use t, and then it will recognize you're talking about parametric. Okay, hey, I invite you. I'm not going to do it here for us. I invite you, go check that out on Desmos, kind of play around with that. It's pretty cool. All right, there is one more bonus video here in 10.1. I'm really excited about it. You're going to see that next.